So, my name is Federtanz, I'm the Herald, and I will give you a little introduction to Kai Kunze, who's currently working in Japan at Keio, and he is going to give a talk about eyewear computing. And this is a really interesting topic because our human brain is not just limited for specific visual processing, but it's actually kind of, you could say, it is doing things on its own. It is processing things on its own. And this aim in the end is to maybe enhance the computing we do by specific devices, such as, for example, eyewear. And he's going to talk about the beginnings of that. And so give a big round of applause for Kai Kunze.
Thank you very much. The mic is on. Can I get my slides? So for me, it's always, I give a lot of talks, but for me, being here at the Chaos Communication Congress is always special, so I'm also a little bit nervous, and I hope that I won't be wasting your time for the next 25 minutes or so on. So the topic I want to talk to you about today is eyewear computing, augmenting the human mind. As mentioned, I'm working at Keio Media Design, Keio University in Yokohama, Japan. And before I start to give you an overview, I'll show you a quick demo, because beforehand I had some problems with Bluetooth in this room, so I think now the demo works. So what you see here, I'm currently wearing a prototype from Jin, from a Japanese glasses maker, and it uses electrodes to measure my eye movements, and you see my live blinks. It also has an accelerometer inside, so you can get also the motion of the head. So I'll go into details how this thing works and what you can do with it also. But because the demo worked right now, I thought it's good to start with it. So let me give you an overview over the talk. So first I give you a little bit of background about myself. Then I'll go into details why I think eyewear computing is interesting or something to explore. And then I'll talk about how we can make it accessible so we can use it every day, and normal people, not only us geeks, can use it, especially enabling technologies like electrooculography. And then I'll give a little bit of an outlook on how we can be able to measure other cognitive states, something like cognitive workload or so on in real life. But that's more or less an outlook, and we just started with this work. So as a background, I worked in wearable computing, and this means, I used mostly motion sensors and other sensors. I put them on users and tried to figure out what they're doing. My former supervisor, Paul, you see him here in this picture, calls it a Christmas tree setup, because we put a lot of sensors on the people and try to figure out what they're doing, and try to support them during everyday tasks, so doing maintenance work, but also sports. And a lot of my work was trying to figure out how we can get from these dedicated sensors towards something you can wear with your smartphone, or sensors that are embedded in everyday garment. And then, since the last 2 years, I got more and more interested in what's going on in our mind. So can I also detect cognitive states or cognitive activities? And in this case, the eyes got more and more interesting. I started with EEG, and I found, I'm a little bit lazy, so I found it too difficult to make sense out of EEG signals. And the eyes were another way to observe the mind, because, they are we use them every day. We use them even while we're sleeping, even when we have our eyes closed. They're still moving. And there's a lot of work in psychology and cognitive science and other related fields that link eye movement to something like attention, concentration, intention, and higher cognitive tasks. But unfortunately, most of the eye gaze today is used for something like this, so for advertisement, marketing. And now that we have mobile eye trackers, you also do this in supermarkets and figure out how your product must look like that people will pick it up. And I think that's a waste, and that's a little bit sad. So last year, I gave a talk about tracking reading habits. So in this case, we used a mobile eye tracker from SMI. This is also an optical system using infrared lights. You see on the top the view on the eyes. And infrared cameras underneath your eyes to detect your pupils, and with this you can recognize your gaze and you get saccades, so fast eye movements and fixations out. And with this we can recognize reading, and we can tell how many words you read. And not only this, but we can also figure out what kind of document types you're reading just by looking at the visual behavior. And that's important for Japanese students. We can distinguish science books versus mangas. And and also we slowly try to assess how much you understand, so comprehension, but that's trickier or more difficult. That was last year. And you could already build some kind of Fitbit for the mind. I'm not really sure if you want to have this. You could get your reading count during the day, how many words, with what speed you're reading, how many mangas versus science papers. But I'm wondering myself, what are healthy reading habits? How can I improve my reading habits? What happens if I copy somebody's reading over 2 or 3 years? Will this make me an expert in a certain field? The biggest problem I see right now with this approach using the technology I introduced last year is, first of all, this just works for reading. So I would like also to have something more general, so focusing on attention, concentration, focus in real life settings. And the other thing is, it should work during every day. And the biggest problem there is the mobile eye tracker you see over here. It's not something you would like to wear, and maybe some people would like to wear it, and then the next problem is then also the battery power. The device is not so, you can maybe record 4 hours or 5 hours in one go. And so we focused already on tablets and smartphones, but then the problem comes that, okay, if you turn this tablet off, it's not working anymore, so you don't have a coverage of the whole day. So we try to implement eye tracking on these devices. It also doesn't work so well with a front-facing camera. The computer vision is quite complicated, but we did also some work on Google Glass, although it's not maybe social acceptable everywhere. There are more problems in Germany if you walk around with Google Glass than there are in Japan. So it depends also a little bit on the cultural background, but you can do some stuff with it. And now I want to show a demo, a little bit an extension from last year's work on glass. So basically, glass doesn't have an eye tracker, but it has a small infrared sensor over here that's used to detect if you wear the device or not. And also you can have a long blink to take pictures, which I find here. What you see right now is the picture I see on the head-mounted display in glass, and you have this touchpad on the side, so I can see all pictures I took. I taped over the camera, so if I take a picture right now, you should see it just shows black and a little white dot because there's the light sensor, otherwise I cannot see anything on the display. So what we did with it, we have an open source glass logger that logs all of the sensors from the device, and we can also monitor the infrared sensor. So this is something I showed last year already. This is a little bit an advanced version, and you can also recognize, so if I move my pupil and don't blink, okay, some of the things are detected as eye blinks, but you can see also the light, the infrared sensor moves, so you can detect something like left and right movement of the eye from the change of the distance to glass. And now A little bit more advanced demo. What can you do with it? For one, I can do some very limited activity recognition with it. So after maybe 2 or 3 seconds, it should show what I'm currently doing. This is just a 2-class segmentation problem. So currently it says talking. And now, if I focus here. So reading, this just uses my head motion as well as the eye blinks to detect, to distinguish talking and reading. Talking works relatively stable during the day. Reading is a little bit troublesome with the infrared sensor because of, if you're watching a movie or so on, it might also say talking, reading, because that's not working so well. But other things you can do with eye blinks, as I mentioned, one is recognizing talking. So this is simple because your blink frequency will increase, usually double. And there are also some correlation with focus. So usually if you focus on something, your blink frequency will decrease. And also with content. So what I observed is if you look at people reading from an e-ink display, you recognize that they blink when they turn the page. And I would like to use also the change blindness during blink. I haven't really gotten a good idea what I want to do with it, but you probably know that if you have some kind of stimulus or if you blink and somebody changes maybe the color of the background or changes some people in here, I wouldn't recognize because I blinked in between. And you could use this, for example, for a display that changes just when you blink. So you wouldn't recognize that something in your view changed, but if you want to get the new information, it's already there. And some ideas like this, and I think it would also be cool for horror games or interactive movies or so on. I think you can really scare somebody with that. And another idea, something that's also fairly simple, is fatigue detection. So just by the duration of blinks and the blink frequency again, so if it gets more higher, you can detect how tired somebody is and how tired somebody will become. And I had the idea of equipping a batch of students with just simple blink detectors for classes, and then have a ranking system of lectures. So you can get the most boring lecture versus the second boring lecture and so on. I tried. I discussed this with some professors at Osaka Prefecture University, the university I was beforehand, and they didn't really like this idea too much. I wonder why. Maybe we can do something at KMD with this. And then other things you can do, blinks together with head motion helps you to distinguish closely related activities. In this case, we recorded reading, watching a video, solving a Sudoku puzzle, sawing to have some physical activity, and also talking. And just with blinking frequency, you get already quite far. You get up to 70%. And then if you include the head motions, you get up to 82%. However, there are some issues also with glass, and even more with the eye tracking hardware. It's first of all power, but also they don't really look so appealing. So it's not something somebody will wear during everyday tasks. So there are new systems from SMI and also Tobii, and they look nicer, but you can already recognize, there are things built by engineers and researchers for engineers and researchers. So for everyday people, for normal people, maybe it's not possible. So I was quite happy when Inami-sensei asked me to join for a project with Jin, a Japanese glasses company, and they make prototypes of Jin's meme, so the glasses I showed you in the beginning, and they have a very different idea from Google Glass. So this is not a full-fledged computer on your head. It has no display, it has no camera, and the device is just connected to your phone. So currently it's just streaming data to your phone. One is the electrooculography and the other one is motion sensors. So with one you can detect eye movements, left, right, up, down, and also eye blinks. And the other one, accelerometer and gyro. And we're directly working with them in the research department. And on one thing I was also happy, so on one side I can work on smart glasses, on the other side for some promotion video I could wear the optical camouflage from Inami Sensei, so win-win situation. Yeah, the demo, insert the demo here, so you already saw it. And now I go into the principles, how it works. So we use electrooculography. Basically your eye is a dipole. It has a positive charge in the front, a negative in the back. And if you place electrodes around your eye, you can measure eye movement. So the regular setup is like this. You use an electrode on the top of your eye and an electrode below your eye to get the vertical movement, and one left and right to get the horizontal movement, and usually one reference one. The advantage compared to optical eye tracking, you can run very high sampling rates. You have no problems or not so much problems with battery power because you don't need so much processing. And some of the disadvantages are it's just relative eye movement, and it can be sometimes noisy, so it depends also on the skin and so on, and on the electrode placement, of course. There were some other people who worked on this, so you don't really have to use goggles. You can also use headphones. So Manabe-san from Docomo used headphones for that. Or Andreas Burling used also this regular setup with top and bottom for up and down, and left and right here for the horizontal potential measurement. What Jin's meme now did, they integrated it into normal eyeglasses, so they use a 3-point EOG. Here you see it in detail, and if we can go to the GoPro, I can also show it to you on the video. No? No, okay. So you see these are the 3 electrodes, so you use the left and the right one. For, if I'm not shaking so much, you can actually also see something. The left and the right ones for the horizontal axis, and these 2 then for the vertical axis. Okay, back to the slides. Right now, these are just first prototypes, and the battery runtime is around 8 hours streaming data. If we do onboard processing or so on, it will get even better. So now you might wonder what you can do with it. For one, we can recognize the eye movements, as you see here, so blinks and left and right. This was one of the earlier prototypes. That's, by the way, Shoya. He was here last year. Unfortunately, he couldn't join this time. And you know what is the first thing you try to implement? If you have a binary control system like iBlinks, yeah, Flappy Bird, this is really, really, really hard to play. You also see it in the face of Shoya. And I can try it also later, maybe you can try it, but getting even a score of 1 or 2 is hard. What you can also do is, of course, more interesting activity recognition. In this case, we can detect reading, and just by time we assign a word count currently. So this is 15 to 20% error, but of course we can analyze the data further and get better results. So reading and also the talking, so the head motion change as well as the blinking frequency change, easy to detect. So you can get an overview over your day, how much physical activity you did, because it also has an accelerometer inside, but also social interaction and how much reading you did. Now, I think right now they mostly focus for the product or so on. They mostly focus on fatigue detection, and they want to release sometime next year in September. But if you're not into consumer products and so on, or don't want to wait till September and want to build it yourself, it's not so difficult. So there are a couple of instructions online. I was mostly astonished by the iBoard by a Honduran teenager. And his setup really works. So Masai, a student of mine, also built one. He took several of the DIY instruction sets, and he just uses 2 electrodes left and right to detect the horizontal movement. But as you see, it works relatively well. So even small eye movements or so on can be detected with a DIY set. And now, we have to hurry, so just 5 minutes left before questions and answers. Now we are also trying out other EOG setups, other electrode setups, what works best for reading or for other cognitive tasks. And you might wonder, can we use EOG also for this tracking of reading habits, and how does it compare to the optical eye tracker? So in this case, we use a medical EOG with active electrodes, so the one I have equipped there. And just looking at the horizontal component again from the potential, that's a graph you see here for me reading. And I just use a simple peak detection algorithm to detect the line breaks. So these long peaks are the line breaks, and interestingly enough, you can also detect very small line breaks, so kind of 2 or 3 word things. So these are the not so deep peaks. And that's not possible with the optical eye tracker because the sampling rate is not high enough. So that's quite nice. Oh, and by the way, this is not published yet, but as soon as it gets hopefully published, I'll also share the code or so on and share how you can kind of filter or so on the EOG signal. And then for the last part, for the last 5 minutes, I want to talk a little bit about how we can recognize more general cognitive states. In this case, we try to track cognitive load over brain sensing. So we used NIRS, a near-infrared spectroscopy device from Shimadzu, Lab NIRS, and this estimates the oxyhemoglobin change in the blood, in this case in the prefrontal cortex, so the oxygen change in the blood. We used the Lab NIRS, the GINS meme, and an optical eye tracker, a stationary eye tracker device. What you get from the NIRS is brain activation. So the red means high activation, blue or green is lower activation. Strange interface, but yeah. And this is then the eye gaze synced with the brain activation, so in this case a reading task. But what I'm really interested in, we didn't only record reading, but also calculation and some memory games. So in this case, you see a memory task, NBAC, that's a common task to assess memory, and 1BAC is relatively easy, 2BAC gets already quite difficult if you're not trained, 3BAC is more difficult, and 4BAC nearly impossible if you have not trained. And this is a recording from one user. With the workload, as I said, 1 was easy for him. Looking at the FNIRS, 2 was a little bit more difficult, 3 was most difficult, and 4, the person gave up. So, and I'm most interested in this state. If it's possible to detect this state not with a Lab NIRS device, but with something like blinks, eye gaze features, or some other cheap sensors, we can implement something that keeps us challenged while learning and not frustrated. And that's something, I would really like to go. We just recorded the data. I'm not sure if there's something there. I saw some correlations. Pupil diameter is something, but that's not something I can get over the EOG. Blink frequency is also interesting, but it's not good enough to detect this state yet or also predict it, because what I really want to do is I want to predict that if I increase the difficulty for a task, the person will give up. And that brings me more or less already to the summary. So I believe that if you look at the last centuries, the biggest scientific breakthroughs were about our physical limitations. So, we can now travel faster, we can build higher, we live more comfortable, longer lives. And I believe, the future will be about overcoming, or the biggest scientific breakthroughs will be about overcoming our cognitive limitations. And let's work together with, open tools and open code to achieve this. And that brings me also to a quick thank you slide. Just want to name two people, so especially Oliver Amft and Christoph Schuber, who enabled part of the talk because of some hardware I got from him. And a special thanks to the people who actually did the work. So Shoya, Katsuma, and now if you have questions, remarks, or violent dissent, and also if there are people interested in an open eyewear platform or so on, please come and talk to me later.
Thank you for the nice talk. We have We have 5 minutes for questions. You can line up at the microphones. We will start with microphone 4.
Could you explain the blink again? How do you capture that?
So for the blink...
Sorry for the interruption. Please move out quietly. No talking.
Because the eye is a dipole. You said it's a dipole, so it moves down when you blink, or what?
No, blink is actually muscle activity you get also. So what you see here is blink is relatively a nice pike, so kind of this signal in the EEG, and you get it over the muscle movement. So this is not the dipole. So the eye does not move. In this case, you move your muscles, and that's also something you can register over the electrodes. That's actually a, how do you say, a noise signal if you want to recognize EEG.
So you have one kind of sensor capturing muscles and dipole movement of the eyeball.
Yeah. And you also see, I mean, you also have to do some filtering. So if I move my head and so on, of course, you will get this also on the EEG.
Because of the small, okay, thanks.
Yep.
One question from the Signal Angel.
The question was, what sampling rate does the EEG operate with for the line lengths?
So for sampling rates, this depends on, so the Chin's meme currently samples at around 100 hertz. It can go, I think, up to 200 hertz. This has nothing to do with the electrodes, but with the chip inside. And for the line lengths, the data you saw beforehand, that's a medical EEG, so this is 500 hertz. So here you need some higher sampling rates. So for this, you need 500 hertz. But I think maybe with 200 or 150, you would also get reasonable results for line break detection.
Thank you. Microphone number 3.
I was wondering if there's any ethical reflection included in your studies and in your work. Because, well, you don't have to have too much fantasy just to think how this thing, which is funny here, can be used as a perfect tool of control.
Yeah, I agree. And I think there's already a lot of work. That's why I had this advertisement slide. I think we are already behind, some companies that work in this field and have more knowledge about the relation between brain and eye movement and so on, and also kind of how there are whole studies on how to place products or how to design a supermarket or something like that are not out there. And for me, the important part is that the data stays with you. I don't want Google or Apple or somebody like this developing glasses and then getting all of our data, because I'm already scared from the data, just the location data and the other data I'm giving away for free. So there's definitely an issue. I think, one thing we can do is just try to open this research up and show people what is possible to hopefully prevent somebody misusing this. But yeah, that's definitely an issue. Thanks.
Microphone number 2.
Yeah. My question is, are you doing any research to connect your technology with virtual reality? For example, in the field of architecture or in arts?
I'm personally not so much, but there are some people at KMD, so especially Inami Sensei, who worked in virtual reality and also thinks about this. But I had not. So I think especially for virtual reality, I think optical eye tracking is nice or nicer because you can get a relation of where you're seeing, and you don't have this problem. If you're already wearing an Oculus Rift or a similar device, you don't have this problem of having something lightweight or so on to carry. EOG, I'm not so sure. I think this blink thing could be something. The change blindness during blinks could be interesting. But yeah, thanks.
One last question from number 2.
Hi. I wanted to ask you about whether have you thought about capturing brain waves from the frontal cortex, because it seems like something that is around.
So I tried EEG beforehand. So I played with the emotive. I have also the OpenBCI, so the .com thing, not the .org thing. And I was interested in the talks yesterday, but unfortunately I couldn't get in, and I haven't really met the people. From my experience, as I said, EEG is relatively noisy, and it depends highly on users. So for me, surprisingly, it works very well. For a lot of my students, it doesn't really work well because of the placement of the electrodes and so on. So I'm interested, and I look into it. But for me, being lazy, eye gaze seems to be easier to come by and use. Also, I find, FNIRS is also interesting to some part because we saw now that maybe 2 or 3 channels could be enough to detect something. So I definitely look into it. But so far it seemed to be, for me, more difficult than using eye gaze. Thanks.
One last round of applause for Kai.